Mr. Alia, Mr. Herrick, and Professor Firdaus, good morning. My name is Dian Anggraini. You can all call me Dian. Today, after exactly 92 days of accelerating thesis work, I would like to present my thesis on the topic of automated status identification of microscopic images obtained from malaria thin blood smears. My presentation is organized in 4 parts, and I will emphasize on the research methodology and research findings. To begin with, malaria is an infectious disease caused by protozoan parasite from the genus Plasmodium. In Indonesia, the highest prevalence of malaria is found in forest-related areas, including Papua, Kalimantan, and Sulawesi, where access to medical service and practitioner is very limited. This figure on the left illustrates how the Plasmodium infects humans. The red circle here represents red blood cells or erythrocytes, and the small oval object here is the infecting parasite. So the parasite going into the red blood cells and undergo life cycle that includes trypophoid, schizone, and merozoic phase or stage. Its phase is characterized by difference in morphology, size, and presence or absence of several pigments or granules. So remember, the key word is the changes in morphology. Furthermore, World Health Organization recommended that the key to overcome global health problems caused by this disease is through accurate diagnosis. Among different techniques utilized for diagnostic purpose, examining dim-stained blood smear under light microscope is believed to be the most sensitive and specific one. However, this method is very time-consuming and prone to error since it relies heavily on the expertise of the expert microscopists. One way to overcome the drawback of microscopy is through computer-aided diagnosis system that has been proven to help reducing error. Therefore, a lot of research efforts have been put to develop such systems. However, there are several problems with the previous study and in this work, which was collaboratively initiated by the Agency for the Assessment and Application of Technology, along with Eijkman Institute for Molecular Biology, under the incentive respect from Indonesian Ministry of Research and Technology. We tried to develop a CAD system for malaria cases in Indonesia while addressing the issues mentioned before. There are two kinds of blood film used, or two kinds of blood smear used for diagnostic purpose: the thick smear and thin smear. As for the time being, we only focus on the thin smear of Plasmodium falciparum in ring stage. Now, in front of you is the microphotograph or the image of blood smear that become the input of our system. The main goal is actually to identify the infected red blood cells. This is the one, which means that it has parasite inside it. However, as you can see here, not all erythrocytes are infected. There are also white blood cells and platelets and artifacts, also red blood cells that has artifact in it that actually convolute the identification process. All images were captured using a digital camera that is specifically built for the light microscope. One problem commonly found with previous study is that the images are either unstandardized, taken from data banks, scanned, copied, or even used in vitro cultured parasite. Our work is superior in the way that we work side by side with experts from Eijkman Institute for Molecular Biology in the development of the data set. So they prepare the images and analyze the images. Therefore, for each copy of the image, we have the original copy along with the analyzed copy, so we can always refer back to the analyzed copy. We propose a standard image processing scheme that processes the captured image and extracts important and relevant information to further classify each image as negative or positive. This is our testing environment. Furthermore, in this study, we try to develop a CAD system that, unlike the one proposed in the previous study, actually embrace the mechanism of manual microscopy. This figure actually represents the steps used by expert microscopy when they analyze blood image. This might look a little bit complicated, and actually the clearer one is in the handout. I prepared that already. But the main idea is this. So, human operator will first try to identify red blood cells. This is red blood cells, and red blood cells. And when they try to determine whether it is infected or not, they will try to find two basic and most important constituents of the parasite, namely its nucleus, the blood spot here, and the cytoplasm, which is characterized by the presence of a large sac-wall, which is the lighter area here. So remember, the key is the black spot and the lighter area. Therefore, we try to translate this very knowledge into an image processing algorithm, and this will be explained in great detail. The algorithm is developed using several selected images and trained using 60 images and tested using 20 images. Blood microprotographs actually exhibit some degree of color variability, and we found that grayscale compression followed by 5x5 median filter actually removes the noise and without compromising with the parasite detail. So it removes the noise that we do not want to be in the image, but it did not delay the parasite detail. As for identifying of the blood cell components, each image, the pre-processed image is converted to binary image, then it is subjected to whole filling process, then to connected component extractions in order to find a binary marker that can be used as individual masks while we are analyzing each blood cell's component. The first step of segmentation is accomplished through binarization using OTSU method that separates the foreground objects from the background using a statistical decision theory approach. The figure in the left is the histogram showing intensity distributions of most microphotographs. It can be observed that object and background have pixels that have intensity in two dominant classes. So let's call this C1 and C2, and I illustrate this histogram to this image. With OTSU method, the threshold K here is selected as the one that can maximize the separability between the two classes, or maximize the between class variance according to this equation. OTSU method worked properly for our image. However, due to the big concave nature of erythrocytes, some foreground objects have holes. Therefore, the hole filling is necessary. Our hole filling process, we propose a hole filling process that does not actually use morphological dilation, conditional morphological dilation, but we use connected component extraction. So first, the complement of the binary image is made, then the connected component is labeled via connected component labeling, and then we make the complement of the extracted image that has the widest area to obtain the binary marker. Now, we come to the most challenging but interesting and rewarding part. Our final classification model is built as a two-stage classifier with two sets of features using bias decision rule in each phase. First, the individual cells, or the segmented one, will be classified as negative or possibly infected based on intensity range. Then, the possibly infected one will be classified as negative or positive based on white to black ratio. During the first stage of classifications, we use intensity range, which is the mathematical difference between the maximum and minimum intensity as the feature. We found that infected erythrocyte, this is the range, and erythrocyte with artifacts, this is the range, and healthy erythrocyte, or without parasite without artifact, actually exhibits a significant difference in terms of intensity range. So we believe that we can actually use this as the first feature. This is how we calculated and utilized bias decision rule for the first stage of classification. In the second stage of classification, we try to find the parasite constituents. Trained human operator can easily accomplish this task. However, to translate their knowledge into an image processing scene is not a trivial task. We believe that parasite component is characterized in grayscale image with difference in grayscale intensity as illustrated in this figure. So as you can see here, there are three main regions of intensity: the black spot, the lighter area, and the gray one that represent the components of the cell and the parasites. So if I have this image, I can illustrate the histogram of this image with this one. So as you can see here, there's C1, which is the black spot here, C2 represents the gray